Here we have another practice problem. This is worked example 1.3 in the textbook. We're going to be drawing some structures again, some Lewis structures again. This time we are going to indicate the hybridization. So let's draw those structures. We have CH2O. So this time I don't have the periodic table. I don't have those Lewis structure guidelines pasted here. However, you have those for your notes. Bring those out if you need them. If you don't need them, that's great. You do have like a hint here in terms of the strategy. We know that hydrogen forms 1 bond, carbon forms 4, oxygen forms 2. So carbon, again, almost always going to be in the center. And then we have hydrogen, 2 hydrogens. We're starting off with just a skeletal structure, knowing that hydrogen likes 1 bond. And we draw in the oxygen just with 1 bond until we add in everything we need to add in terms of bond. We know carbon needs 4 bonds. Currently, it only has 3. This is not okay. You look at the hydrogens and you see that they have a bond already. This is the most they can do. They can only do a duet. That's it. However, the oxygen we know needs an octet. It only has 2 electrons around it right now. So we're going to draw in a double bond to the carbon. And then if we were to calculate out the valence electrons and everything, what we would have is 4 valence electrons left over. And these are actually the non-bonding or lone pair electrons that go on oxygen. So this is the structure of CH2O. And this is actually formaldehyde. You probably heard about this. You probably smelled this in biolab if you've taken biolab. So what are the hybridized orbitals around this? Remember, let's think about those parking spots. And let me switch colors. We need 1 spot here. That's not the color I needed. There we go. We have 1 parking spot there, 1 parking spot there, another right here. We need 3 spots. And we know that S is always just 1 orbital. And we know that P has 3. We need 3 spots. So what we're going to do is take 1, 2, 3. And together that forms sp2. So around the hydrogen here, and I'm going to clean this up for clarity. Around that carbon right there, we have sp2 hybridized orbitals. Here we see the solution, and we can see the structure we drew, the Lewis structure we drew. And this is the only way that the 2 hydrogens, the carbon and the oxygen, can combine in a manner that fulfills the octet rule and the duet rule for hydrogen. So like the carbon atoms in ethylene, the carbon in formaldehyde is in a double bond and its orbitals are sp2 hybridized, like we predicted or like we solved. So this is just a comparison of the different types of bonds that we see specifically in methane, ethane, ethylene, and acetylene. Here in methane, all we have are sp3ch bonds. So we have just 1 number for each of these for the bond strength and the bond length. In ethane, we have single sp3 overlapping carbon-carbon bonds. And then we have sp3ch bonds. You can see that the CH bond they all have their own unique numbers, is what I am trying to say and trying to demonstrate. And you can see here that as the number of bonds increases, so from a single bond to a double bond, in ethane to ethylene, the carbon to carbon, right? This is single, this is double. The bond length is going to decrease because the bond strength is also getting stronger. It takes more energy to break this bond, and it creates more energy when it's formed. And you can see the same thing in comparison from the triple bond to the double bond. It's stronger, and it's also even shorter because there's more electrons overlapping. What happens when you have lone pairs? So you may have noticed that on that oxygen, we had some lone pairs. However, that was not directly on the central atom. But what happens when you have lone pairs on the central atom? So for example, this NH3, we have, or this is CH3NH2, methylamine. Here we have a carbon, CH3 group, hydrogen, hydrogen, nitrogen central. We have a lone pair above this nitrogen. What is going to happen to the bond angles? This is actually an sp3 hybridization. sp3 hybridization is associated to being a tetrahedron or tetrahedral around the central atom, and that is usually associated to being a 109.5 degree angle when you have the exact same type of bond around the central atom. But here we have different types of bonds. We have an NH, a lone pair, a CH3. So we can see the bond angles are different. In addition, this lone pair is actually pushing down because lone pairs want as much space as they can have. And it's repelling and pushing these bonds a little bit closer to each other. The same thing with this oxygen, which also has sp3 hybridization around it, but its bond angles are smaller than 109.5 because these lone pairs are really affecting those bond angles. Same thing here with this methane thiol compound. The bond angles are really tiny at 96.5 compared to 109.5, again with this dimethyl sulfide. So there's many examples that you can look at here. So now we are going to view a simulation that includes real molecules that shows the effect of lone pairs. So once you open up the simulation, you should see the option for model or real molecules. We are going to look at real molecules. So here we have water, and we are showing the lone pairs, and we are going to want to click to show bond angles and also electron geometry. So this is a tetrahedron in terms of electron geometry, meaning how many things are around that central atom. There's 4, right? There's 2 lone pairs and 2 bonding pairs. Remember, the ideal, or the, not affected by lone pairs or different types of bonds, is 109.5 bond angle. Here we see that it's less, it's 104.5 because we have those lone pairs pushing down, trying to get more space for themselves. Let's look at NH3, which we were looking at a similar compound, not exactly the same, but pretty similar. Here we see that we have 1 lone pair at the top. The bond angles, instead of being 109.5, they are 107 because the lone pairs are pushing down. Let's look at another example. Let's look at CO2. So this is actually not really showing lone pairs. All this is showing you is how something could be completely linear if you have 2 symmetrical bonds around each other. Here we don't have a lone pair, so it's actually following the ideal or the, quote unquote perfect bond angle. So those are some different examples. You can go ahead and check some more out. Here's that ideal tetrahedron, 109.5, but yeah, you can go ahead and check a bunch of these out and look at them for yourself, and also maybe brush up on electron geometry and molecular geometry. So we've reached the final boss of the bonding theories, which is molecular orbital theory. This is the most complicated orbital or bonding theory, but it explains some bonding situations, some magnetism situations that the other bonding theories can't. So that's the whole reason we have more than one bonding theory. All this really is kind of some same ideas where, you know, we have the energy level, we have lower energy level versus higher energy level. We always typically want lower energy. It means more stable. So here we have two 1s orbitals where they combine and they form a bonding molecular orbital, right? These are atomic orbitals, the atom by itself versus a molecular orbital. So here we have an S bonding molecular orbital where both electrons are, you know, behaving nice. They are filling that orbital that's now combined to form a bond, versus whenever they're a little, you know, too close, they can be called anti-bonding. So they're not filling that bond. And you can have the same thing with p orbitals overlapping, where the p bonding molecular orbital is filled versus not filled.